let's work out an example of arc length. So let's try to find the arc length of the following function. F of x equals e to the x between x equals 0 and x equals 1. So the picture that we have in here is that we have the graph for the function e to the x, and we're looking for the length of these p's between x equals 0 and x equals 1. So we want to know what is the length of that blue piece. So for that, we use the expression for arc length, which is the integral between a and b of the square root of 1 plus the derivative of our function squared dx. That means that in our case, what we have is the following thing. We have that the derivative of our function is just e to the x, and we just have to put it into our expression. That means that what we're looking for is the integral between 0 and 1 of 1 plus e to the 2x dx. Here what we have is that the derivative squared will be just e to the x squared, which gives us the e to the 2x part in here. So we can tackle this integral by doing a u substitution. So we can set the substitution to be e to the 2x. That means we can do u equals e to the 2x, which gives us that du is equal to 2 e to the 2x dx. And notice that we can rewrite this part, we can write down the exponential again as a u. In other words, we have that this is the same thing as 2u du. That means that we can write down the original expression as the integral of 1 plus u, and then we have dx is the same thing as du divided by 2u. Now we can also translate the limits of integration. So 0 and 1, we have that for x equals 0, that gives us that u equals 1, and that for x equals 1, this gives us u equals e squared. So that means that we can write down the whole integral in terms of u, so that way we don't have to go back in x whenever we finish. In other words, the expression that we have in here is 1/2 the integral 1 to e squared square root of 1 plus u divided by u du. So this is a nicer looking integral, but still we don't have something that we can easily work with. So a common trick is to actually go ahead and do another u substitution. We can do a nice substitution in here by setting v to be 1 plus u. So this will make our integral to look a little bit nicer. We have that with this substitution, then this integral becomes 1/2 square root of v divided by v minus 1 dv. So notice that here we just wrote from the original substitution, we have that u equals v minus 1. Now this will affect our limits, because whenever u equals 1, v will be equal to 2. Whenever u equals e squared, that makes v to be e squared plus 1. So now the integral that we're looking at is 1/2 from 2 to e squared plus 1 square root of v over v minus 1. Again, this one looks nicer, but still we are not in a good position to work it out. So let's do another substitution. Let's do w equals the square root of v. So that will make dw to be 1 over 2 times square root of v dv. But notice that this bottom part, the square root of v, that is the precise same definition as w. So this becomes just 1 over 2w dv. So that means that we can translate this integral to be 1/2 the integral of w divided by w squared minus 1, and then dv is nothing else but 2 times w dw. So notice that this integral looks nicer now, and we actually could have done that from the beginning if we look at this expression and set w to be the square root of 1 plus e squared. We could have done all these three u substitutions in the same step, but I think that is nicer to see how we can actually do the same method a couple times and still get a very nice result in the end. So in here, I just need to translate the bounds. So we would have that our integration bounds would be square root of 2 and square root of e squared plus 1. Again, if v equals 2, that means that using our substitution, w means square root of 2. And if v equals e squared plus 1, then we have that w is going to be the square root of that. So in the end, the 2's cancel, and we have a very nice expression in the end. This will be square root of 2, square root of e squared plus 1, w squared minus 1 dw. So now this one, we can work it out using integration, using partial fraction decomposition. And this, since we have the same degree on the top and the bottom, would require long division. We can simplify this expression by working it out using long division, which is the same thing as writing it down using this relationship right here. So notice that if I gather this part, that part is just 1. So I will get 1 plus 1 over w squared minus 1. That's the same result that I would get from long division. So I have this integral to be the integral between square root of 2 and square root of e squared plus 1. 1 plus 1 over w squared minus 1 dw. Now from here, we can apply partial fraction decomposition for the last part of that integral. So by that, what I mean is that we can write it down as 1 over w squared minus 1 is a over w minus 1 plus b over w plus 1. And then we should be able to find a to be 1/2 and b to be negative 1/2. Again, after doing the partial fraction decomposition, that's the answer that we would expect. So that means that we can write down our original expression as the integral between the square root of 2 and the square root of e squared plus 1. 1 plus 1/2 w minus 1 minus 1/2 w plus 1 dw. And this is an integral that we can easily work out because this becomes w plus 1/2 the natural log of w minus 1 minus 1/2 the natural log of w plus 1. Everything between the square root of 2 and the square root of e squared plus 1. So the only thing that I have to do is I have to plug back the top and the bottom into my expression, and that would be the answer. That means that this ends up being the square root of e squared plus 1 plus 1/2 natural log of the square root of e squared plus 1 minus 1 minus 1/2 the natural log of e squared plus 1 plus 1. That's the top limit, minus the bottom limit, which will be square root of 2 plus 1/2 natural log of the square root of 2 minus 1 minus 1/2 the natural log of the square root of 2 plus 1. And even though this expression looks pretty lengthy, this is just a number, and that number represents the length of the curve that we had here originally. So that is the arc length between x equals 0 and x equals 1.